In lesson 8, we're going to continue what we did in lesson 7. Actually, in lesson 8, we're going to define an actual 3D model, because if you remember from lesson 7, that was we examined two different cases for a beam. The first one was its own weight, and the second one was weight and temperature difference with this cross-section area and the height of 300 millimeters. But when I did the analysis with a beam 3 element in here, and when I represented a 3D representation or model of the analysis, we saw that conservation of mass or volume was not taken into account in the analysis. So basically in lesson 8, I'm going to do the same thing. A beam hanging from the ceiling of the same height of 300 millimeters, and the cross-section area of this is okay, I'm gonna delete that one. The cross-section area of 12 by 12. The same material with elasticity of 200 gigapascals, Poisson's ratio of 0.3, density of 7,800 kilograms per cubic meter, and coefficient of thermal expansion of 13 times to the minus 6 for either Celsius or Kelvin. They're both the same. But today what's going to matter, what's going to be different is that instead of doing a 2D model, I'm going to do a 3D model. So I'm actually going to make a 3D model and apply the boundary condition and the gravity of 9.8 meters per square second. And then I'm going to apply the same temperature difference of 30, either Celsius or Kelvin, and see how the beam deforms based on these two different cases. And we will also see how the area of this beam changes as it elongates based on its weight and the temperature. So with that, let's go to ANSYS and do the analysis. Okay. In ANSYS, the first thing I want to do again is to go to preferences and make sure that I'm doing a structural analysis. And then the next step is to define the elements for my analysis. Come to here, and for lesson 7 we came to beam and picked beam 3, but here for this analysis, for example, I'm going to pick solid, scroll down and pick tetra 10 node 187. So it has a tetragonal element shape with 10 nodes per element that I'm going to pick, and click OK. Options, I'm going to stick to the defaults and OK this window. And go to this element does not have any real constants, so if I pick here and click OK, it's going to tell me that solid 187 element type does not require any real constant, so I just close this window and go to material properties. Come to material models, and like lesson 7, the first thing I want to do is to define the Poisson's ratio and elasticity. So, and then density of 7,800 and thermal expansion of 13 times 10 to the minus 6 is the values that we're gonna use. The next step is to generate the model. So I come to modeling and create, and because I'm gonna do a 3D analysis, so I come to volumes, a block, and by dimensions. I want to give from minus 6 to plus 6 for x, from 0 to 300 for y, and from -6 to +6 for z. So this gives me a square cross section of 12 by 12 and a height for the cube of, or yeah, the cube of 300 millimeters. I click OK and my beam is made. I can switch to isometric or oblique, and I pick this one. The next step is to mesh this model because we used volume. We need to divide our model into number of nodes and elements. Because my ANSYS is a little bit limited to 10,000 elements per analysis, I should be a little bit careful because otherwise I will face an error. But if you have a better ANSYS to work with, you can um, do a finer meshing than what I'm doing in here. I come to Mesh Tools, pick Smart Size, and go to 3, Mesh, and click select my volume and click OK, and I hope that, yep. Well, the meshing that you see in here, if I zoom in it, is not perfect for this analysis. But again, if I want to make a finer meshing for my analysis, I'm going to face an error because of the limit that my version of ANSYS has. But if you have a better ANSYS, just you won't be worried about this one, so you can just mesh your model to as many elements as you can or as you want. Now that meshing is done, come to loads. I want to make sure that I'm doing a static analysis. Click OK. I come to define loads and apply structural. The first thing I want to do is displacement, and I want to make sure that this area is not moving. So I come to on areas, pick the top area, click OK, all DOF 0, which means that that area is not going to be moving in either of the X, Y, or Z directions. I click OK, and then the next step is to define the gravity. Come to inertia, gravity, global, in Y direction 9.8, click OK, and the first step is done. So I come to solution, solve, current LS, and the solution is done. Now let's see how my model deforms based on its own load now. Plot results, deformed shape. Let's keep the deformed plus undeformed. And let's zoom in a little bit. And let's see from the front side. And also let's look at nodal solution in Y direction. If you look more carefully, you see that the length of my SAM or model in X direction and also in Z direction is shrinking as my model is elongated in a Y direction. So let's see the deformation in X direction. The deformation is very small because of the small cross-section area compared to the height of my model, but there is some deformation in X direction if you look carefully in here. And then let's see stresses in Y direction. Again, it's somehow similar to what we saw yesterday, except for today because of my meshing. It's not as precise as the model in lesson 7. But something you want to pay attention to is the fixed end. It's not a constant stress in here. As you see in the middle, there is a little bit difference compared to the edges of the sample. And it's because as the material is expanding in its height direction, it's about to shrink in its cross section, so it's about to shrink in X and Z directions, and because of that it's facing some stresses in these two directions, and that's why we don't see a constant stress in here. Let's see vector plot and translation of U. If I zoom to the top, see this very small um, translation. Zoom back and to the bottom, the maximum displacement is happening in the bottom where it's free to elongate. And let's see what happens with reaction solutions, all items. Here I have a number of results for fx, fy, and fz. If you remember from yesterday, the fx and fz were 0 and we only had an fy, plus there was only one node that was given to me for the results. But here I have a number of nodes and number of values for fx and fy, and if you look carefully, they're not even small values. It's minus 0.36 times 10 to the 8, which is pretty high. So what you see in here is um, this probably this is more accurate in analyzing a beam and its deflection based on its own weight, or even if it's uh, external loads, compared to yesterday's or lesson 7's example, which was completely engineering analysis without taking into account the change in cross-section area of the material as it expands because of its own weight. So let's get back to solution and add the temperature difference to the volume. Come to here, pick volume and enter 30 for temperature. And let's rerun the solution. Alright. Let's switch back to deformed shape. And let's see how it deforms. Slightly different. And this time it's also expanding in x and y direction, x and z directions, because we have temperature difference. So the expansion, because of applying temperature, is probably bigger and stronger than shrinking due to elongation because of weight. Let's zoom back and go to contour plots, nodal solution, and in y, you read the values in here, and also you can see in x direction, it's a little bit more um, uniform and organized than before. And let's also see predefined translation in vector. It's again something similar to the previous example, but the values are a little bit bigger now than they were in the weight alone without any temperatures. We can come to list results, reaction solution, and find the results. See them in here. The reason that the loads in here are very close to the loads that we read for a case without the temperature is that the temperature is not actually applying any forces to the material. The only thing that happens is that the temperature is applying thermal stresses, and they're not showing up as external loads that will be read as a reaction and the fixed end. So well, actually these are 10 times, I guess, greater than the ones that we read before. But if you remember from lesson 7, there was no difference between the reactions in this fixed end with or without temperature. Let's go to select entities, pick areas, and pick the top area, click OK, and again nodes attached to the areas and all, OK. And let's see if I can get anything from the nodal solution. I want to see stresses in y direction. It's only, yep, the Sx and Sy and all the shear stresses and um, uh, normal stresses are given to me in here. So basically, this is, I can say, the conclusion of this lesson. It's similar to what we did in lesson 7, except for here we generated the 3D model from the beginning and applied the same material properties and the same loading conditions and read the deformation and loads at every step or every um, uh, location of this model. The only thing I want to again mention in here is that because of the limit that my ANSYS has to only 10,000 elements per analysis, I didn't go ahead and do a fine and accurate meshing in order to avoid an error. But in order to get precise results from the analysis, you need to have a better version of ANSYS which doesn't have a limit of 10,000 or a number of elements per analysis. With this, I'm concluding lesson 8.